All right, so so in this problem, look at what happened at the end of the nozzle. This happened when the nozzle is not working at its design condition. If this nozzle was working at its design condition, you all remember the graph, huh? That the supersonic expansion, the flow will leave supersonically with pressure equal to B back. That's the design condition. Now, if you go with a pressure that's not B back, a little bit higher, a little bit lower, we said that supersonic flow, still supersonic flow exit, max 3. So the back pressure is not high enough to put a normal shock inside your nozzle. No, it still have supersonic exit, so that plane is still supersonic. But the pressure is a little bit higher or the pressure is a little bit lower. So what will happen? The flow need to adjust to the background pressure, and because he's supersonic, he will have to adjust either by the way he basically adjusts. If you want to increase his pressure, he will have to go through an oblique shock wave. If you want to reduce his pressure, he do it by an expansion fan. That's how supersonic flow respond to lower pressure or higher pressure. Okay, so what you are seeing over here is basically the supersonic flow trying to get to this back pressure, right? But in his attempt to actually adjust to the back pressure, he either go away from the center line or go inward toward the center line. Either way, whether he's going away like in this case or going inward, yes, that adjusts the back pressure. So in this first attempt, he is on the right pressure now. Okay, that pressure is equal to back pressure, but he's getting away from the center. That doesn't really work well. You cannot just leave the center. Or in case the pressure, basically he was trying to increase his pressure, he will go through an oblique shock wave. This way he is actually compressed inward. So either way, whether he's going away from the nozzle or from the center line or going inward toward the center line, eventually he run into a conflict that I cannot just go through myself. I will have to straighten up. Look, he straightened up here. So how does a flow, supersonic flow going inward straighten up? By oblique shock wave. See, it's as if you are pushing him into itself. That basically increases pressure. So he straightened up by an oblique shock wave, which, what does it do? It increases pressure. Okay, it increases pressure. So now his pressure is higher than B back. After he was in the right pressure, now, but wrong direction. Now he's with the right direction, but wrong pressure, a little bit higher. So he needs to lower his pressure. He needs to lower again to be back. How does he do this? With an expansion fan.
And that's how we get those separated.
And this is how we can get those basically diamond shape behind the jet engine. So let's track this process from the start. So over here, this nozzle have B exit higher than B back. This is this case I'm plotting over here. Look, it's leaving with M exit and P exit. This M exit supersonic, max 3, whatever, depending on the area ratio. And the pressure here is higher than B back. Let's say it's 200 kilopascal. And this is 100 kilopascal. So how can he drop to 100 kilopascal? By expansion fan. Okay, by the way, this is approximated as a 2D, not an axis metric. So in 2D, basically an expansion fan will get launched from the top, an expansion fan will launch it from the bottom, doing what? Removing this extra pressure, going from 200 to 100, for example. Okay, so he turned away, and we had a problem last week in the class. We finished the class with when we solved the direction. Remember, we said he was leaving with that pressure. He need to relax this new pressure. What was the turning he need to go to? And how do we do this? The one and only equation for an expansion fan.
Yep. Turning angle.
Turning angle, and we wanted the turning angle. So obviously we need the two Mach number. Mach number at 1 before the shock, we know it. That is basically the exit Mach number. And the Mach number after the shock, someone had a free quiz for it last week. Who got that? Remember? Or free homework? Someone said, let's use, was it John? He said P over P naught. Right? or maybe Andrew, someone said, let's get P over P naught, and that will allow us to know the Mach number after the expansion fan. How did they get P over P naught after the expansion fan? Well, P is easy. That's the P back. That's what the expansion fan was doing. But how about P naught? And that was the free homework. The free homework was because he said P naught is the same P naught as 1, is the same as P naught as inside the nozzle. Because the expansion fan is isentropic. Nothing gets lost in it. So it's P naught all the way. P naught from the tank to the conversion part. That P naught basically is all the way from here to here to here. Right? Point is, now the expansion fan, the one on top and the one on the bottom, make the pressure the right place. It's P back. But he's leaving away from each other. This means that you will basically create kind of vacuum. You can't. You have to straighten up. So this would be as if the expansion fan reflected from the floor, so that you can straighten up. Okay? Why? Because again, you want basically to straighten him up. So it's kind of, he expanded him to go upward, and then he expanded him again, so that he can go straight, lowering his pressure. Right? We will visit this again today when we talk about the exit of a scramjet engine. Right? But basically, an expansion fan reflects from the floor as an expansion fan. And that's what you see here in this homework problem at the end. Look at this. Expansion fan. Why there's an expansion fan here? Because of the turning, because that 10 degree. Suddenly the upper wall is moved away 10 degree. So that Mach 2, say the exit of the combustor or something, find 10 degree. So what will happen? Expansion fan. Well, that flow going like this, will start now in this place moving with the 10 degree. That's the new direction. He cannot leave the floor. He will try to come like this, moving at 10, but then this reflection from the floor, it's basically to straighten up the flow. So the flow basically, after he was going up, he will straighten up again. So it will be as if you are turning him, giving him more area again. Okay? This is equivalent to basically having another 10 degree down there. It's basically 10 degree and 10 degree, and that's the center line between them. So what happened? He straightened up, and how much, if I want to solve the pressure over here, I want to know how low it will get. How am I going to do this? The one and only equation. I don't have anything else when it comes to expansion. I have to use this equation. So if I'm asking you to give me that pressure here, and I'm telling you have to use this equation, what do you know? Obviously, you don't know the Mach number after the expansion fan. That's why you're trying to, because you're solving for that pressure. That's the unknown. We know the Mach number before the second expansion fan. We know the Mach number here, right? We just solved for it when we solved the first one. So we know that Mach number. So obviously we need the turning. We need to know the turning so that we can solve for the Mach number after the expansion fan. So that is the question. What is the turning? Excellent. Excellent. The turning is exactly the same as the first turning, because here he moved from horizontal to, let's say, 7 up, and here he will have to move from 7 up to horizontal again. Okay? This is kind of the mirror image of, or the evil twin of, the oblique shock wave reflecting from the floor. Remember when an oblique shock wave was reflecting on the floor? He was going in the floor with 7 degree, for example, and then after the reflection, he will have to straighten up. So it's compression, compression. This one is expansion and expansion. Okay? So this way you will calculate this pressure, how low it is. It will be lower than back pressure, because here you have back pressure. So this guy will be lower than back pressure. Right? And you are going straight that's the right direction, but the pressure is low. So what happened when the flow reached the outer boundary? So this outer boundary, that imaginary line over here, huh? This is not a pipe. This is just an imaginary edge where the pressure get adjusted to the ambient. So basically when the flow reached that edge, he basically realized that, it's ambient pressure. We need to go back to ambient pressure. So when this expansion fan hit over here with its low pressure, and here is back pressure, it need to reflect as an oblique shock wave, so that guy go back again to back pressure that he was once at, right? So this go back to back pressure, but of course as a result of those oblique shock wave, he start going inward, right? So yes, you got the pressure right, but now you have the wrong direction, and so when you go inward, that shock wave will reflect as shock wave, making your pressure higher but straightening you up. Now we have the right pressure. No, we have the wrong pressure. We have higher pressure but straight. So it come here to the corner, and we need to relieve that pressure. We need to adjust to back pressure again. So an expansion fan, so that we can go to B equal P back in this place. So when you look to this, basically here is the easy way to do it. 1 year in the exam, I just give them that sketch, but I deleted everything, and basically I just told them, I deleted all the pressure. I just told them, tell me in every region whether the pressure is equal to B back, higher than B back, lower than B back. That's it. So they just basically have to follow the story, you know. I mean, obviously you are expanding, so this pressure must be higher than this guy, higher than B back, and this is B back. And then you're expanding again. This must be lower than B back. And this must compress you again to B back. And so they follow the story. But here is an easy way also to realize what's going on. At the center line, it's as if it's a wall. The center line is really like a wall separating the two flow. So the wave reflects with its own type. An expansion fan reflects as expansion fan. Oblique shock wave reflects as oblique shock wave. Expansion fan reflects as expansion fan. But at the free boundary, at the pressure boundary, the wave always changes its shape. So expansion become oblique, the oblique become expansion. Alright? Does this make sense? Now here is a confusing part, and that's what this homework is asking about. The confusing part is, what do you call this nozzle? Do you call this nozzle overexpanded or underexpanded nozzle? So it's underexpanded because it's written over here, right? But let's understand why it's called underexpanded. So what is the range of operation for that nozzle? It should work from what to what? Ideally. Ideally, this nozzle should work from expand the pressure from. What are the two limits?
Subsonic solution for the Mach number.
No, I want you to just tell me from B naught to B back. Ideally, this nozzle, this is what's available for it. You had this tank or that combustor or whatever the source sitting at P naught, and you had the ambient sitting at P back. So ideally, if they made the area big enough, they would have expanded all the way to this, and this would be their design condition. They make all that, but look at this. They finished here. So what do you call that? Underexpanded or overexpanded? Under, because they could have went much further. An overexpanded nozzle would look something like this. So what happened here? So they have P naught, and they went further down than B back. Alright? So this is the exit. And B back is over here. So what will happen is the nozzle will get adjusted to this back pressure outside. Right. It has to compress with an oblique shock wave. But not this pressure has to be a little bit lower than the limit, which is a normal shock wave at the exit. See, if the pressure, if B back go up to this, then you don't have a supersonic exit anymore. You have a normal shock. And we solved this before. Huh? Remember when we asked basically about what is, that was in the midterm, kind of, what is the range of back pressure that will make this nozzle shock free? Or so it's the last back pressure that put a normal shock at the exit. Anything lower than that, the compression happen outside. And it happened like this. Oblique shock wave that will do what? Will compress you. So this guy is moving now with B equal to B back. So that's the right pressure. Ouch. Obviously in this place, B was higher or lower than B back? Lower than B back. And here you compress it, but you are moving inward. That's not nice. So you straighten up, but what's the price? The price is that the pressure here is higher than B back. So once the flow touch the exit, the free boundary, he basically expand with an expansion fan that will take him outward, but it adjusts its pressure. So here the pressure is B back. Okay, and that free boundary or the pressure boundary I'm referring to something like this, where the flow basically touch the ambient and get adjusted to it. But the point is, this basically keep going forever. Huh? Not really forever, because the oblique shock waves are not isentropic. They kill your P naught. Right. They kill the stagnation pressure. So eventually the stagnation pressure, imagine if the stagnation pressure become B back. I mean, eventually that's what will happen if you keep eating my P naught. Then my P naught become B back. Then what? It's my velocity. Right? And on top of that too, once the flow starts to slow down, the Mach number starts to slow down, he's slowing because of all those shocks. Right? Yes, he speed up, but then the shock kind of kill him. And eventually, once he's small enough, there will be no oblique shock wave. You can basically end up with a normal shock, for example, at the wall. You will not be able to reflect with an oblique shock wave. You need a high Mach number to do this. So eventually, this run out of energy, right? And so when you look at the exit of those supersonic jets, you see, I don't know how many, but like 6, 7. Yeah, we will. All right. Okay, you got it? So what is the questions? Huh? It's something like this, and he basically say, this in the nozzle shown before, it's an underexpanded for the spec pressure, reservoir pressure combination is basically this scenario. Is it underexpanded or overexpanded or operating at design condition? Obviously not operating at design condition. Design condition shouldn't have any of those things. You have perfect supersonic exit. I'll let you think which one is it. All right? And this one, I mean, obviously the reflection from the wall is to straighten the flow, so that, yes, the upper wall would like you to go up, but the lower wall would like you to keep straight. And so that's what happened. Huh? So he will turn like this, go up, and then over here he will straighten, and very good. So in this chapter, he basically would like us to calculate the lift and the drag, okay, and the lift and drag in dimensionless form, which we call them dimension CD and CL, drag coefficient and lift coefficient. So the first step is just to get the pressure, and that's what you did in homework 7, right? So you basically go over every corner and say expansion fan, oblique shock wave, okay, and then you solve the expansion fan and oblique shock wave by basically, here is the equation for the expansion fan, right? And you solve for the pressure, and then you solve the lower shock wave, all right? So after you get those two pressures, so for example in this problem number 9, he said for this 2-dimensional plate, find the angle of attack. He gave us the theta and he's asking us for the delta. This is the delta, right? This angle of attack is the delta for this guy. Can we do that? If we have the M1 and the theta, can we get the delta? From D1. And there's actually really nice equation to get delta straight. Where is it? One of you just asked me about it in the break. What's your name? Zach, show me that equation. Where is the equation for delta theta? Page. So at the bottom of page 200, you can get delta directly from M1 and theta. Right? Page 200 at the bottom. Or use D1. Alright? So once you have delta, then this just become our quiz. Right? You did this quiz. You know basically the drill, and here is the solution again, more and more. The more the merrier. From delta we get theta, get M1 normal. From M1 normal we go to a normal shock table, get the pressure ratio, and that will allow us to get that pressure. Okay? So now once we get the pressure at the lower surface and the pressure at the upper surface, that's not the force, that's just the pressure. The unit is, for the pressure, is Pascal. To get the forces, I need Newton. So I need to turn the pressure into a force, pressure force. So I multiply the pressure by area. Okay? So multiply the pressure by the area. So the area here is the chord C. Let's give it the symbol C. And it's 10 centimeter. So C is 10 and the area is chord time the depths. How deep this thing go into the paper. Right? So we can actually write it per unit depths. If you only provided a 2D section of the problem, we basically say assuming a unit depth, or you can basically, when you get the pressure force, you basically say it's Newton per meter, and that meter you mean per unit depth. Right? And so the left force eventually that we'll calculate will also be per unit depth. If he doesn't provide you the depth, how deep this thing is, Sean.
So the pressure per unit area is not the actual lift force yet?
Not yet. Not yet. This is just the pressure force. We'll do the left in the next page. This is the pressure force on the upper surface. This is the pressure force on the lower surface. So again, in the homework, the first problem which you did, you calculated those pressure before. Now to calculate the pressure force, the pressure here multiplied by 0.2 time the unit depth. That would be the pressure force. Over here, that pressure should be multiplied by 0.2. No, you have to calculate that length. Right? That length is not 0.2. What's 0.2? 0.2 is basically this. It's this part. So in that triangle that have an angle 7.5, 0.2 is this. And you need to basically say it's 0.2 cosine 7.5. Sorry, this is the 0.2. And cosine 15 would be the 0.2 over this. And you want to get that length. Right? Just plot this triangle basically. Alright? So basically the pressure force is simply the pressure times the area this pressure is acting on. And of course it's normal to the surface. So whatever the angle of the surface, the pressure force is always normal to the surface. Of course. So now here is the lift and the drag. So the upper surface have B3 times C times 1. Let me write time 1. Time 1. And the lower surface has B2 times C times 1. So now what is the lift and the drag? Because we fly normal to the gravity, we are really interested in the vertical component of that force. So those two guys together make an aerodynamic force. And that aerodynamic force could be in any direction. But we choose to split that aerodynamic force. So that aerodynamic, you can imagine, if my cell phone is flying like this supersonically, you can guess that he will have a force in this direction, right? Because of the geometry. He will have a force in that direction. It turned out most of the time that the vertical component is very useful. The horizontal component is very annoying. Why? Why the vertical component is very useful?
Because that's giving you the lift up to that.
Right, because it overcomes the weight, which is always down. So you would use this to basically carry this and keep you from crashing down. And this guy is annoying because that's opposing to your direction of motion. So it will slow you down. And so in order to kill this, or not kill this guy, but basically to make him not to slow us down, we have to provide what? Thrust. So that's what those propeller are doing, that's what the jet engine is doing, that whatever your thrust mechanism is. So the thrust need to be equal to this so that this can keep working to carry this. And you basically keep flying at that speed, right? So notice one thing, that the drag we are calculating, the horizontal force we are calculating, so obviously we're going to split this two pressure into horizontal and vertical, take all the vertical together, that's those guy. Take all the horizontal together, that's those guy. This will become the pressure drag. This is the drag due to the pressure that we just calculated, right? So is there any other drag beside the pressure drag? Yeah, friction drag. You can imagine if that plate move like this, you probably will not really have that much pressure difference on top and the bottom. They will be the same. So will that mean that he can really fly supersonically without any resistance because the pressure is equal? No, there is skin friction drag. Where is the skin friction drag? That is in the, if I plot my plate that's flying horizontally, there will be something called the boundary layer. It's in that region. It's very small, few millimeters. That's where the shear and the viscous drag is happening. This is not in this course. This is in when you take experimental fluid in the spring. 4273, you'll be able to calculate this. So really that drag, if you want to do a good job, you would call it DP. You are trying to remind yourself that's only the pressure drag. On top of that, there is a skin friction drag that we are not calculating. All right? And that the drag coefficient that we will calculate in a second, which is going to be CD, we will call it CDP. It's the drag coefficient only due to the pressure. Right? So let me look at this equation first, and then I'll get your question. So what is this? Where is this coming from? So here is B3. C. I want to split it into horizontal and vertical. All right? So the question is always, what is the angle between the force, the pressure force, and the vertical? That's what you will do also here. So in every one of those surfaces, after you calculate the pressure, what you want to find out is the angle between the pressure force that I'm trying to point to its direction and the vertical. Okay? Why? Because once you do this, once you know the angle between the force and the vertical, all you have to do is to say the left would be this cosine this angle because it's next to it, and the drag would be this force sine this angle. Okay? So now to find the angle between this and the vertical, it's much easier to find the angle between the surface and the horizontal. So the surface and the horizontal will trap the same angle as the pressure force and the vertical. How come? Because the pressure is normal to the surface and the vertical is normal to the horizontal. So any two lines that tracking an angle 5, 7, if you rotate them 90 degrees, both of them track the same angle. Right? So it's much easier to find out the angle between the surface and the horizontal. I mean, let's go to that homework. What is the angle between this and the horizontal? 10. Very easily, right? So obviously the pressure force on it will also have 10 degrees with its vertical. The left would be the pressure force cosine 10, and the drag would be the pressure force How about this guy? What's the angle this guy is making with the horizontal? Excellent. 10 plus 7.5. See how easy it is? So now the pressure force acting on it will have 17.5 with the horizontal, with the vertical. Okay, how about this guy? What's the angle this is making with the horizontal? Excellent. Because he went up 10 and then you go down 7.5. So he's still hanging 2.5 on top of the horizontal. Okay? So once every surface you basically find out what his angle with the horizontal, that would be the force, or that would be the angle between his pressure force and the vertical. Alright? So now when you add the left force, of course anything pointing down would be minus. And anything pointing up, that would be plus left. And when it comes to the drag, anything that's pointing against, basically against the flow, sorry, with the, with the flow direction, that will be plus drag, right? This is plus drag, but this is negative drag. This is as if it's providing a thrust for us. So what I'm saying is that you add them with their sign. You can basically just tell yourself, up is plus, down is minus. That's it. Everything up, plus, plus, plus. Anything down, minus, minus, minus. Anything. So it's kind of, you should imagine x and y, and that's it. And so if it's in that direction, that's plus. If it's that direction, that's plus. That's my plus drag. That's my plus left. Sean, you had a question?
You cleared it up. I didn't see the minus sign in the papers. I changed those.
All right. Good. All right, guys. So things become complicated when they start having a lot of surfaces, but it's the same idea. Okay? Same idea. Basically, you try to find out shock or expansion, shock or expansion. This will always have expansion. There is no question that here, in this diamond shape, you will have expansion here. Why? Because you suddenly have a lot of area. So you can count on two expansion fins. It's those two guys, right? And so sometime it will be oblique shock wave, sometime it could be nothing. Sometime it could be even expansion fan if you tilt too much, right? So just find the angle here. Solve for the pressures, realize that the pressure is always normal to the area, and then find out the angle the surface is making with the horizontal. And that would be the angle that the pressure is making with the vertical. After you calculate the left and the drag, here's how you do the left coefficient. So the left coefficient, this, you don't have to memorize this. This is actually in your book. And so, what page is this?
271.
Page 271?
Mm-hmm.
So you will find that the left is, the left coefficient is the left over a dimensionless left. Okay? So this, why this is useful then? Because if you have this left for a certain geometry, if you blow up this thing, bigger scale, the left will be different. But the CL should remain the same. That's why people love dimensionless numbers, because they will be function of the geometry. So whether it's this small or this big, you still have the same CL. You get a small Prius, baby Prius, and you put it in the wind tunnel and you test it. It will be the same, hopefully the same CD, like the big Prius, the real live Prius.
That's where they do scale model.
Right, if you do the scaling right. If the baby Prius, is excellent copy. Not like Dr. Evil and Mini-Me, that's not an excellent copy. Right? You have to have it exactly the same, everything exactly the same. Then you will get the CL to be constant between the two of them. Right? So CL is L over, this is, actually when you think about it, what is that? That's how much pressure in the free air. Half rho V infinity square. That's kind of the kinetic energy in the free air. So it's the dynamic pressure basically, right? That's the dynamic pressure, we call it dynamic pressure, multiplied by C. Yeah, and it should be multiplied by 1 too, but obviously this guy is per unit length, so that's why this is Newton per meter. So that's why they only divide over the C. This is half rho V infinity square C. So actually it's really hard to put your hand on V infinity, because those problems usually he give you the Mach number and P infinity. So it turned out for our advantage that, and we proved this one time, and it's very easy to prove again. If you look to the lecture note, I think chapter 3, we proved this. So half rho v infinity square is the same as gamma p infinity m infinity square. So of course this is more easier because we already know gamma for air, and the problem usually come with p infinity and m infinity. And what's even nicer is if the problem doesn't tell you what is p infinity, you just said this thing is flying at Mach 2. Find the lift coefficient. And you would like, but what is the pressure? That happened actually 1 year, so I didn't give him B infinity. And so everyone started coming to me, where is B infinity? Where is B infinity? I said, you don't need it. I'm like, why? You have to have it. I cannot solve the problem. So I told them, okay, B infinity is 20. Go. Why you don't need it? If you are not trying to get the lift, you just get the lift coefficient. Why you don't need the actual value of B infinity? Because you can solve this by knowing the angle. You just get P2 over P1, P3 over P2, everything will be in terms of B infinity. And then when it come here, yes, the lift, you don't have the lift as 5 kilonewton, but you have the lift as 0.1 P infinity plus 0.3 P infinity minus 0.7 P infinity divided by P infinity. They all cancel out. All right? And that explained to us what's also this idea about dimensionless, that once you have CL, whether you are flying at this pressure or that pressure, as long as the Mach number is the same, you should get the same CL. So that Prius, when you put it, the small one, when you put it in the wind tunnel, as long as the Reynolds number is the same, like the real thing, you should get the same CD. It doesn't really matter what is the velocity of the model and what's the velocity of the real thing. As long as you maintain that same dimensionless number, that makes difference in the problem. Right? So, in this problem, you actually know the pressure, so you don't have to worry about this. I'm just telling you that it didn't really matter what is the number here. You either way, whether it's 20 or 10, you will still end up with the same CL and CD. Okay? Questions? All right, and again, I'd like to stress that what we are calculating is CDP, and this is DP. That's only the pressure part of the drag, not the viscous drag. All right? So let's see an example. So this actually was a midterm, I think last year probably. This problem 15 our textbook also. So he said calculate the lift and the drag coefficient, okay, for that airfoil, Mach number 2.5, angle of attack 5, okay, and see, he didn't give us the P infinity. He didn't mention what's P infinity. Why? It doesn't matter, right? All we have to do is get the solution. If this is 1, 2, 3, and 4, all you have to do is get the pressure 2 and 3 and 4 in terms of P infinity. And eventually the CL will cancel the P infinity with each other. So let's solve it very quickly. So what happened at the front?
You're going to have a mop at the bottom of the area.
So Sean said expansion fan at the top. Does anyone agree with that? No. Why? Steve. So Steve basically looked at this and he said, this is 5, and then this is another 5. That must make this guy straight. So what happened then at the top? Nothing. Still P infinity. And then, of course, here, I don't have to think about this. This is always expansion fan. Right? And the turning is, I need the number. 5, Steve have 5. Anything higher? 10. John is right. 10 degree. So how do we get this angle? Okay, so in any triangle, this angle is always beta 1 plus beta 2. This angle, the one that we care about, the turning, is always those two guys together. So if this is 7 and 5, this is 12. If this is 1 and 2, this is 3. Why? Because this and this make 180. And those three guys make 180. So it must be that this is always this plus this. Okay? Does this make sense? So anyway, so turning with 10. How about the bottom? What do you have at the bottom? Expansion or oblique shock wave? Bottom?
The bottom, you got an oblique shock.
Right, of course, oblique shock wave. And the deflection is, delta is 5 degree. Why? Because the difference between before and after, right? Before was horizontal and after it's basically this guy. That's the direction now. And this guy is 5. Okay? So see, those things are the difficulty that you will see in the midterm. Is basically what is the angle that, so I can start my expansion fan calculation or I can start my oblique shock wave calculation. Of course, if you are weak in calculating the expansion fan or oblique shock wave, that's another disaster waiting. Right? So obviously nothing at the top, expansion fan, and we are saying the turning is 10 degree, delta is 5, a shock wave. You go and calculate the shock wave, M and delta, you get theta, you get M1 normal, you go to normal shock table, get the pressure ratio, you got the pressure over here. And see now the pressure is 1.37 P infinity. But what is P infinity? We don't know. We don't care. Let's just keep it as 1.3 P infinity. Why we don't care? Because we are not calculating the left. We're calculating the left coefficient. So it will cancel. P infinity will cancel. On the top, 10 degree, one and only equation, always use it. Turning is nu2 minus nu1. You know the Mach number before, you want to get the Mach number and the pressure after. Okay, with the turning. So 39 and 10, that's 49. This is how you can calculate M2, obviously from appendix E. And from that you get P2 over P1 equal to 0.4885. Right? This is again B2 over P infinity. That's all you care about. And then putting the pressure forces normal to the surface. So every surface has pressure force normal to it. Okay? And before we calculate the left, you have to split this pressure into vertical and horizontal. So you need the angle between the pressure and the vertical. Obviously this guy is horizontal, P infinity is vertical. That's all left, minus left, no drag, right? And so this guy, this is making 5 degree, that is the chord, so of course it's making 5, so this must be 5, right? So B3 would be, B3 cosine would be this, B3 sine would be this. Same thing over here, B2, and see how B3 and B2, they are all in term of B infinity, 0.4 B infinity, 1.3 B infinity. And so you put those guys here with plus or sine, you divide over this, and B infinity cancel with B infinity, and you get your CL and CD. Questions? So here is the cosine for the left, plus, minus, minus, and here is the CL, and here is the drag, okay, plus, minus. So this is plus and this is minus, plus the B3 minus this guy, right? And of course this guy, this should be horizontal. Not doing good job. This is supposed to look horizontal. Ouch.
That makes it look better.
How about this? Right? So the horizontal guy doesn't show up in the drag, only those two guys. And look at the lengths that they are multiplied with. So this P2 multiplied by not the chord, not the chord over 2. This P2 is multiplied by this. How do I get this length? Out of this triangle. So out of this triangle, this angle is 5, and this is C over 2. So that's why it's C over 2 cosine 5. Okay? So now a reminder is that for a flat plate, there is an equation that will calculate for us directly the CL and CD, and that equation is on page 270. So we calculate the left on page 270, the left and the drag. And it say be upper and be lower. Does everyone see it?
No.
So my problem is, and that happened with many times, I will give them an airfoil like this. And they would use this equation. Why would they use this equation? I mean, obviously it's wrong. Why?
Because it's not flat.
Because this equation is only for a flat, right? And when you want to use it also, what is the B upper? Is it, I mean, this guy, or even in your homework, for example, like I will give them something like this, and they would say that you would just use this equation. And that's when 1 year I told them, I'm going to give you in the midterm an airfoil, and it's not going to be a flat plate, and please don't use this equation. This equation is only for a flat plate. And if anyone uses this equation, I'm going to kill myself. And to my surprise, one guy used it. Fortunately, I was smart enough. I didn't kill myself. The equation on page 270. All right? Of course, if it happened to be a flat plate, go ahead and use it, right? It's for a flat plate. That's why there's only one pressure on the top, one pressure at the bottom. But for anything that's like this, okay, or like this, it doesn't work. You have to basically work the pressures and divide them. But there are certain shortcuts, okay? So for example, you know, when you try to calculate the pressure, first you split it and then you multiply by the area. A shortcut is basically say the vertical component would be the whole pressure time the projected area. So that would be equivalent to, let me get the full pressure, split it into a component and multiply by the true lengths. When you do this, it's exactly the same as, let's not split the pressure into vertical and horizontal component. And let's not even multiply by the true lengths of the, because sometimes the length is hard to get. Let's just multiply the pressure time the projected area. Okay? So if you want to get the vertical component of the pressure force on that surface, you multiply the whole pressure time the projected component of the area in the vertical direction. Okay? If whatever make it easier for you, use it, all right? Okay. This was once also in an exam, and I told them calculate the lift coefficient. And I give them very little time actually to solve this problem. I mean like 1 minute or something. Why I give them so much time, so little time?
What was the question?
Calculate the lift coefficient.
0.
Excellent. Symmetric.
Technically,
The lift would be the difference between the forces in the vertical direction. You add all the vertical direction, and that would be the lift. So if you really want to solve this, you know it's an oblique shock, and then what? Expansion fan, and you solve all the pressure. But guess what? What is B1 and B2? Exactly the same, right? And B3 and B4 will be exactly the same. So at the end of the day, the upper and the lower surfaces will match. And so when you try to calculate the left, it will be 0. And therefore the CL also is 0. Right? 0 over whatever is 0. So for symmetry, basically, you will not have any left, but you have drag. So obviously something like this will have to generate left. What you need to do? You need to have an angle of attack so that you would kill that symmetry, basically. Right? Right. So, but here he didn't ask for the left coefficient because that will be silly, right? That's only for the midterm. You ask a silly question. But in the homework problem 11, not homework problem, in our book, this problem number 11, he said calculate the drag coefficient. Because he know that there is a drag. Yes, there is no left, but there is a drag. There is pressure drag. Okay? So you have to solve the oblique shock wave, the expansion fan. You don't have to solve those two guys. right? And so it's basically just putting your hand on the deflection for the seed for the shock wave and the turning angle for the expansion fan. So obviously for the first shock wave on top and the bottom, the delta is this delta, this capital delta, right? It's the 5.7. How did I get this angle? He gave me the what? He gave me the thickness to the chord ratio, 2 over C. You see, you don't see it from this. Let me just clean it. See, he said the T over C equal to 0.1. How is that helpful? That's the T and that's the C. You do the tan angle, right? So the tan would be basically this over this. Half the length, half the thickness over half the chord, or basically also 0.1. So tan delta is 0.1. From that you can get this delta. It turned out to be 5.7. Okay? So remember this, you need to work a little bit the geometry of the airfoil to get the right angle. And so once you solve the flow on the top, you don't really need to solve the flow at the bottom. All you have to do is that similarly, the pressure here will be exactly the pressure here. So when it comes to the drag, the guy on the top will also contribute the same way like the guy at the bottom, to the extent that you just say the contribution of the guy from the top and you multiply this by 2. Right? When it comes to the drag, it's just basically that pressure times his area multiplied by 2 for up and down. And for the expansion fan here, how much is the turning? 2 delta. We already decided that, right? We said that this angle is always this plus this. So for symmetric airfoil, if this was delta, this also will be delta. Good. So the answer is CD is 0.012. Try this at home so that you can practice to do this quickly. All right? Questions for the drag on the left? So that they can use the same idea to actually make those things fly. So those hypersonic vehicles, they are basically carried on the shock wave they are basically generating, right? The left, there is no wings. Those are not really wings. Those are kind of controlled surface, right? But the left is generated by the pressure here, right? You can imagine there's pressure here and there's pressure there, right? And it's this pressure, the vertical component of it, that's generating the lift force that's supposed to carry the weight. So in 1 year, I gave them something like this, and I said this hypersonic or supersonic UAV can be approximated as a triangle like this. The weight is this much. How much is the span? How much is the width to be able to carry the weight? So how much is the span to carry the weight? All you have to do is generate the lift per unit depths and say that lift times the depths is equal to the weight. And from that you calculate the depths. Right? So that's why they call it the Air Force version of this. Let's jump to it a little bit for a second. So the Air Force version is called the Wave Rider. So X-51 is called the Wave Rider. And so why it's called the Wave Rider? Because it's ride on the shock wave generated from the front. Exactly. So you can imagine there is pressure, right? And if we approximate the top to be just horizontal, what will happen on the top if it's horizontal? Nothing. If it's horizontal, nothing. If it's horizontal, basically the flow will just keep moving, right? So you got B infinity and you have very high pressure here, and we'll see what will happen at the back in a second. But basically you get all the vertical component, and those should be able to carry that left, supposed to carry the weight. We solved this in homework, right? One home problem, how does reflection work? And so that's a hypersonic inlet, right? Let's remember that there is also the axisymmetric inlet for the Blackbird, right? And this is definitely a subsonic inlet, because if this was flying supersonically, normal shock will form a normal shock. You don't want a normal shock standing over here. And for supersonic, the inlet is always like this for an oblique shock. So you can see here is a MiG-35, for example, and that's the old MiG-25. You can see how it's basically tapered for an oblique shock. So that's a supersonic inlet. And he's saying here that the hypersonic inlet is basically not only you want to absorb the shock, but we also want to increase the velocity. Sorry, you want to increase the pressure inside, so that you would basically get out of the, you don't have to use a compressor. Alright? And now let's look at, we will talk about the combustion inside in chapter 9 and 10 next time. But let's look what happened after the combustion in the expansion. So you will leave the combustor section with very high temperature, and then in all those jet engine, what is the point behind all those jet engine? You want to generate very high velocity so that you can get the thrust, right? You want to basically send the flow at very high velocity. And so you build that pressure in the compressor, you build the temperature in the combustor. The combustion usually happens at constant pressure. Okay? And then you expand in either conversion nozzle or conversion diversion nozzle like rocket engine. So for hypersonic, this is kind of a conversion diversion nozzle. Or basically it's a way for you to go supersonic. You're already supersonic. You want to make it even faster, right? So you want to speed up already say Mach 3 or Mach 2. How do you speed up Mach 2? Well, if you basically open an expansion like this, an expansion fan will come out. The flow would basically, rather than going horizontal, it will tilt with this new wall, right? And then this expansion fan hit the floor, reflect from the floor. That reflection will basically make what? Make the flow straighten up again. But I would like you to look at this, because one year I asked them to plot the velocity vectors inside something like this. So look at that. The expansion fan turn the flow from horizontal to vertical suddenly or gradually? No, gradually. Gradually, right? Unlike the shock wave, right? So unlike the shock wave, where things happen immediately, this guy basically go like this, and then gradually turn into this direction.
Because he turns just a little bit.
Excellent. Because each one of those rays is a little bit, every one of them is Mach wave, Mach wave, Mach wave. So he's gradually turning like this until he go this way. So that's why when it reflects, it also does not turn you immediately horizontal. It's also with each one of them, you gradually straighten up until you leave horizontal. Alright? So this guy, to kill the reflection from the top, what do you need? Because this is as if you are designing what? This is as if you are designing a rocket nozzle. Okay? This part. This is really as if you are designing the exit of the rocket nozzle. So in order to prevent any reflection from here, what do I need to do in that wall? It finished horizontal, that's correct. But here, and the gradual, it should basically be matching this, right? It should match this so that the flow, when the ray come here, there is no reason for it to reflect, because the flow next to it is just exactly like the wall. So that nozzle basically just go with the contour of the flow field. You got it? Yeah. Right, so see this, if let's forget about the orange one. They are not here. What happened? Every one of them just go like this. Every one of them go like this. The last one, if he try to leave the floor, that's a problem. He cannot really leave the floor, because the floor force you to go horizontal, right? How a supersonic flow changes direction from I'm going to go up to going straight? By a reflection. reflection of this Mach wave. So that reflection of the Mach wave, each one of them reflects. See, there are actually tons of them, and that's why there are tons of reflection. So each one of those guys, basically, rather than the last one of them leaving the wall, no, the last one of them just basically keeps straight with the horizontal wall. Excellent. And now to prevent a shock wave coming over here or an shock wave coming here or expansion fan over here, you need to make sure that the pressure here after this, if I call this say 7, 8 and 9, you need to make sure that after those two expansion fan, B9 is B infinity, right, or B back, which happen to be B infinity. Again, the same B infinity. So we compressed from B infinity at the nose to the pressure inside the combustor. We raised the temperature, and then over here, over two expansion fan with the same turning, say 10 and 10, we need to go down again to B infinity. If you don't, then this pressure will not match that pressure, and you will have to go through. And what's the big deal? What will happen outside? Well, the big deal, he basically start taking direction, and you don't jet it. If you want to really send him and get full thrust, you don't want to send him with an angle. You want to get him straight out. Right? So that's what I'm trying to explain over here. That the pressure over here eventually need to be equal to BB ambient. Leaving need to go, otherwise you have under-expanded nozzle or over-expanded nozzle. No, you want to finish at B ambient. If you want to finish with B ambient, that basically tells you what is the temperature at the exit. Right? And also knowing the pressure from here, that it need to be B ambient, right? And knowing B naught over here, because we will learn how to solve this, the combustor part. So if you know P naught here, that's the same as P naught here. Knowing this P naught and this P, you actually know now the Mach number at the exit. Right? So this will allow you to calculate the thrust, and you can work it backward, meaning that if you know how much velocity you need at the exit to generate that thrust you are hoping for, that tells you basically what should be the pressure and the Mach number over here. And that tells you basically how much fuel you need to put in this place. But this is how you solve those things, by basically two turning. Right? And so I'm showing you here basically that solving the from 6 to 7 is the same as 7 to 8. And it's the same angle, same turning. Okay, and so that this will allow you actually, if you know those two Mach number now, if you know I'm leaving the combustor as Mach 2, I want to finish at Mach 8, that basically tell you, well, obviously you need two turning, and those two turning, turning here and here, 10 and 10, for example. That will allow you to figure out how much angle I need to open with. Okay? Right, and so now you generated enough thrust that we should carry the drag, so let's calculate the drag on the left. So the left would be something like this. Okay, so now this pressure is P1, this pressure is P2, this is B infinity, this is B infinity, assuming those two guys basically hit here. And this, you could basically say, well, I'm going from P7 to B8 and I'm doing it gradually, or from B7 to B infinity. Let me assume a linear function, for example, or you can solve for it if you are doing 2D basically, and you're taking every one of them. But you can just assume a linear function. And this eventually then will tell you how much pressure to allow you to calculate the left and whether it will be able to carry the weight of something like this or not. And you also calculate the pressure drag. And you leave it for experimental fluid to calculate the viscous drag for you. Right? And this is a picture for the X51, and it's exactly the same idea. Again, the nose, one edge, second edge, and this thing come in, and you see basically is attached to a solid booster next to it. That's what accelerates him. Alright?